So, anyways, we're starting to think about how far away could our p hat, our sample, be from our parameter. So I've got this nice applet at Rossman Chance. Okay, let's go ahead and assume that we have a proportion, that the real value of a proportion is 0.6. All right, and I'm going to stick with the sample size of 100 because that's nice. And I draw a sample. Well, you'll notice, first of all, on your graph, it starts at 0.44 to 0.76. Now, in theory, all the possible values are anywhere from 0 to 1, but it's narrowed this down to the probable values, and I'll tell you why in a little bit. So if I keep drawing samples, you can see a shape beginning. Let's say I draw 1,000 samples, and you start to see this shape. What do you see? Pretty much you're going to start to see the normal distribution that I was discussing on the previous slide. So how far, as I said before, in theory, any value from 0 to 1 is possible for our sample. Possible, let me be clear on that, for p hat. But not all these values are probable. As you saw, the simulation kind of narrowed the ranges for us. They gave us only the plausible values. Um, since we're using a normal distribution, we can actually use the empirical rule and actually know that, or be able to predict that 99.7% of our point estimates will be within 3 standard deviations, and about 95% will be within 2 standard deviations. So if we wanted to be 100% confident, of course, we could say that our observed proportion will be between 0 and 1, but that's not helpful. If I say, oh, what fraction of the beads are black, and I say, oh, it's anywhere from 0 to 1, then I haven't really impressed you. But if I kind of lower my confidence level a little bit, and I'll talk more about that, we can be more precise in our prediction. And in fact, a confidence level of 95% is frequently used. It provides a pretty high level of confidence and significantly tightens our window. So what is the confidence level? In a way, you can see it as specifying what percent of our samples will be predicted to lie in this window. So we're like, oh, okay, we want to capture about 95% of the samples. And they will be in the middle of our sampling distribution. The critical value, Z star, and that's a lot like the Z we worked with before in normal distributions, fences off the expected lowest and highest values that would contain C% of the samples. Okay, so to find our critical value, if you may recall, when we would try to find z-scores from probabilities, we would use the inverse norm function right here, that inverse norm. And one thing to keep in mind, it's going to, whatever your thing is on the, when you draw your bell curve, all right, and wherever your z value is, it's going to take whatever's on the left. It uses the area to the left of that z value. So see how I have this arrow drawn here? It's that area that will give it that critical value. If I wanted that critical value, I'd actually have to have this white and blue area put together. Good news for you, I've actually figured out, well, it's easy, figured out a shortcut formula that can help you determine your z-score for any confidence level. All right. So if I want a, let's say a 50% confidence level, I have only 50% of my samples in the middle. It's not a very good level, but we're going to use it. How much do I have left for the outsides? Well, I have a total of 50% left for the outsides. So 25% would go here and 25% would go here, right? So I basically said, oh, 100% minus 50% and split it in two. Which, and if this was, say, I wanted the middle 60%, I'd have 40% left over after I took it up from 100%, and I'd have to divide it in two. So I do 20%. So I do 1 minus the confidence level and divide by 2 and do inverse norm. Now I go ahead and put the absolute value on this because this is going to tend to give you the left z-score, the critical value. And normally we were talking about it in a positive value. Again, this shortcut I gave you is not on your math chart. So if you want to use it, you need to memorize it. So if we were using the most popular confidence level, 95%, here I go 1 minus 0.95 and then divide by 2 Remember to divide this by 2, not just the 0.95. So that's inverse norm of 0.025, right? That makes sense. 5% is left over. Divide by 2, that's 2.5%. And you would get the value z equals 1.96, right? By the way, this is a very frequently used value and is worth memorizing as well. In fact, that's probably worth more memorizing than that, but it wouldn't be hurt to do both. Now, if I had been tempted for a 95% confidence level to do inverse norm of 0.95 or even 0.05, I'm going to get the wrong value because that's not how much that area is going to be. I have to subtract that middle part from 100% and divide by 2. So make sure you use this to calculate your area. So let's go ahead and do 2 quick examples. We're going to calculate the critical value for a 99% confidence level. Well, since I gave you the formula, it's going to make it a lot easier. 1 minus 0.99. There's 1% outside of the 99%. Split it into both sides. So you have a 0.5% in each side, which is 0.005, and our critical value would be 2.58. If I had done this without absolute values, I would probably actually get negative 2.58, but we're just going to use the positive value. If I'm doing 90%, okay, so 90% is in the middle. That leaves 10% outside, split it in half, so 5% is actually here. So I would do inverse norm of 0.05, and I would get 1.645. One thing to keep in mind, as the confidence level increases, the width of your interval is also going to increase. Remember, I could do 100% confidence interval, and then my width covers the whole thing, which is not useful. If I go down to a 99% confidence level, I'll still have kind of a broad one, but not too bad, depending on sample size. If I go to 95%, it's going to contract even more. In fact, you can remember that for 99%, it's about 3 sigma. For 95%, it's about 2 sigma. So you can see the factor changes from 3 to 2. So that's some decent shortening or narrowing of the confidence interval.